Black holes are among the most perplexing and strange phenomena in the universe. They remain the focus of intense examination and interest among experts in space, astronomers, and physicists alike. Characterized by enormous gravitational pull and a complete lack of light emission, black holes represent a limit that cannot be exceeded. The established rules of physical science no longer apply here, as Albert Einstein first hypothesized in 1916. As a direct result of black holes, the theory of general relativity was born. They remained purely theoretical until advancements in 20th-century technology allowed for their indirect detection. A pivotal moment occurred during the 1960s, when researchers studying the Cygnus constellation accidentally discovered an unusual celestial object, a bright blue star emitting a large amount of X-rays. The star's orbit around an invisible partner defied conventional explanation until it became clear that it was gravitationally bound to a massive black hole, now known as Cygnus X1. This discovery provided crystal-clear evidence that black holes exist and marked the beginning of a new era in scientific inquiry into these cosmic enigmas. Cygnus X1, located approximately 6,000 light-years from Earth, is extremely dense and possesses such a powerful gravitational force that nothing, not even light, can escape it. Its defining feature gave it its name. Since then, numerous black holes have been discovered throughout the universe. Estimates suggest that there could be more than 100 million in the Milky Way alone. Despite their massive scale, the elusive nature of black holes has made direct detection a struggle. Astronomers have identified several candidates within our galaxy, from stellar mass black holes formed from the remnants of massive stars to supermassive black holes at the centers of galaxies. Black holes profoundly affect space and time, extending their influence beyond their immediate surroundings. They shape cosmic structures and impact the fate of matter in their environments. Any object that ventures too close is inevitably drawn toward the event horizon, the boundary beyond which escape is impossible. Objects that cross this threshold are affected by powerful tidal forces and are eventually consumed by the singularity at the black hole's center. This catastrophic process, known as extreme spaghettification, is a manifestation of intense gravity. As an object approaches the event horizon, the gravitational gradient along its length stretches it into spaghetti-like strands. The black hole's forces overwhelm the internal bonds holding the object together, resulting in disintegration into a stream of matter that ultimately merges with the singularity. The allure of black holes as laboratories for pushing the limits of physics remains irresistible. Though still shrouded in mystery, the quest to understand them continues, driven by a desire to grasp the fundamental nature of gravity and the vast scale of the universe. Black holes stand as silent sentinels, beckoning humanity to explore the unknown and expand our understanding. Despite the enormous distance, the closest known black hole being about 1,500 light-years away, questions about their potential effects persist. In 2021, researchers achieved a significant milestone, the first clear image of a black hole, specifically M87, located in the center of the M87 galaxy. This remarkable accomplishment provided critical insights into the nature and elusiveness of black holes. The visual data revealed that black holes have intricate layers, challenging the conventional view of them as simple, featureless voids. Through detailed imaging, scientists identified three distinct layers. 1. The event horizon, the outermost boundary marking the point of no return. Once this limit is crossed, the gravitational forces become inescapable. 2. The photon sphere, a region where light orbits the black hole. Photons entering this zone are trapped by gravity and can circle indefinitely. 3. The singularity, the core of the black hole, where the laws of physics break down, and all known scientific principles cease to function. Each black hole, while sharing this three-layered structure, has unique characteristics and behaviors that defy simple classification. Traditional scientific methods often fall short in studying these massive cosmic entities, making innovative approaches and indirect observations essential. Direct exploration is impossible due to the extreme gravitational forces that would destroy any probe. Still, researchers persist in their quest to unlock black holes' mysteries. Theories abound, from stellar collapse to complex cosmic dynamics, offering intriguing insights into their behavior and origins. For instance, NASA's investigation of the M87 galaxy provided compelling evidence for a supermassive black hole exerting gravitational influence on a cosmic scale. Despite these challenges, the pursuit of knowledge remains relentless, fueled by human curiosity and a drive to understand the universe. While black holes defy easy comprehension, scientific commitment promises to illuminate the darkest corners of the cosmos. A breakthrough came in 1963 with the work of Roy Kerr, who proposed a model that redefined black holes as never-ceasingly spinning objects. His theory introduced the ergosphere, a region around a rotating black hole where spacetime is dragged along, preventing anything from remaining stationary. This model revealed deviations from classical physics and hinted at deeper mysteries within. One particularly fascinating implication of Kerr's theory was the prediction of Einstein-Rosen bridges, or wormholes, hypothetical passages through spacetime connecting distant parts of the universe, or even parallel universes. Wormholes arise from the interaction of Einstein's general relativity and the geometry of the spacetime fabric, potentially allowing for faster-than-light travel across vast cosmic distances. However, the practicality and stability of wormholes remain topics of intense debate. Their intrinsic instability, combined with quantum forces and radiation, casts doubt on their viability as travel conduits. Furthermore, general relativity imposes limits on the speed of travel through spacetime, meaning even stable wormholes might not enable faster-than-light movement. Still, the concept remains a staple of science fiction, and theoretical exploration continues to inspire bold new ideas. Despite the speculative nature of many theories, the study of black holes continues to push the frontiers of modern science, offering glimpses into the fundamental nature of reality. The enigmatic nature of black holes has also prompted the fusion of multiple scientific disciplines, astrophysics, quantum mechanics, thermodynamics, and information theory, to understand what truly happens inside and around them. One of the most provocative developments in recent decades has been the black hole information paradox, a concept brought to prominence by physicist Stephen Hawking. According to Hawking's groundbreaking work, black holes are not entirely black. Instead, they emit a faint type of radiation now known as Hawking radiation, due to quantum effects near the event horizon. Over time, this radiation causes black holes to lose mass and eventually evaporate. But this poses a serious problem. If a black hole can disappear, what happens to all the information about the matter it consumed? In classical physics, information is never truly lost. However, if black holes evaporate completely, it challenges one of the core tenets of quantum mechanics, that information must be conserved. This paradox has ignited a fierce debate and driven research into reconciling general relativity and quantum physics, potentially pointing toward a unified theory of quantum gravity. One proposed resolution is the holographic principle, which suggests that all the information falling into a black hole is not lost but encoded on its surface, the event horizon, much like a hologram. This principle proposes that the entire three-dimensional information about objects inside the black hole can be represented on a two-dimensional boundary. If true, this would revolutionize our understanding of the nature of reality, implying that the universe itself might be a vast hologram. While these ideas remain theoretical, they have profound implications not only for cosmology but for the foundations of physics itself. The search for a theory of everything, which would seamlessly unify the forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, continues to draw heavily from what we observe and hypothesize about black holes. Black holes, far from being mere cosmic anomalies, have become central figures in our pursuit of ultimate knowledge. They are no longer seen solely as destructive voids but as gateways to understanding, intense laboratories where the limits of physical laws are tested. Their study has inspired not only scientific research but also philosophy, raising deep questions about time, reality, and the fate of all matter. As instruments grow more advanced, from the Event Horizon Telescope to planned space observatories like LISA, Laser Interferometer Space Antenna, scientists hope to glean even more insights into the behavior of black holes. Future missions may help detect gravitational waves from black hole mergers with even greater precision, revealing clues about the universe's birth and structure. Ultimately, black holes continue to captivate the imagination and intellect of humanity. They are cosmic riddles that challenge our understanding, stretch the boundaries of science, and whisper secrets from the edge of space and time. In their silent, powerful presence, they remind us that the universe is still full of unknowns, and that the journey to uncover its truths has only just begun. Impeding the enticement of wormholes persists as a shining example of scientific curiosity and investigation. The idea of the wormhole, which got its name from its pioneer scholar, exemplifies the tempting promise of alternate cosmic portals and facts that call humanity to think about the mysteries of the universe and contemplate the inconceivable possibilities beyond. The search for a single theory that brings together gravity, regions that appear to be spread out, and the rise of quantum mechanics has sought an explanation for everything, a comprehensive system that can unify all fundamental forces and the universe's particles. At the forefront of this endeavor stands Myoku, a well-known theoretical physicist whose groundbreaking work has helped propel the study of superstring theory. The superstring theory marks a significant deviation from standard ideal models. It assumes that fundamental particles are not point-like entities but rather tiny strings in motion. These strings, similar to those of musical instruments, vibrate at particular frequencies, which give rise to the different forces and particles found in nature. In this paradigm, the universe is transformed into a great orchestra, with each particle corresponding to a distinct harmonic resonance of these fundamental strings. One of the most striking implications of superstring theory lies in its capacity to explain mysterious events associated with wormholes, black holes, and other exotic solutions to Einstein's equations of gravity. As the strings run through the fabric of space, their fluid movement leads to the development of gravitational anomalies, topological distortions, and singularities. Despite the elegance of superstring theories, they conceal inherent complexity. They call for the existence of dimensions that go beyond the familiar three dimensions of space and one of time. These extra dimensions, hidden from direct observation, challenge our intuition. Nevertheless, scientists use models, like the analogy of fish living in a two-dimensional lake, to give a glimpse into the elusive nature of these higher-dimensional beings. The consolidation of these additional dimensions, such as folding a sheet of paper into a roll, makes them difficult to notice at everyday scales. Yet, their influence is felt throughout the very fabric of reality. The exact nature of these subterranean dimensions remains elusive in concept. However, their presence offers a promising explanation for the oddities and complex structures observed throughout the universe. The mathematical foundations of superstring theory have sparked a revival in both physics and mathematics, demonstrating deep connections between dynamic mathematical patterns and physical phenomena. In fact, the search for a theory of everything has become a catalyst for combining various fields, illuminating the intricate interaction between mathematics and the natural sciences. Despite its scientific precision and theoretical beauty, superstring theory remains an untested framework in need of experimental confirmation. The elusive nature of additional dimensions constitutes a formidable obstacle, relegating experimental verification of the theory to the realm of mathematical speculation. Nevertheless, the outrageous vision of superstring theory continues to captivate the minds of enthusiasts and researchers alike, enticing people to embark on journeys of intellectual exploration. As we venture deeper into the unknown areas of theoretical physics, guided by the illuminating insights of superstring theory, we are presented with the mysteries of the vast universe, poised at the dawn of a new era of understanding. Physicists continue to unravel the secrets of quantum black holes, a phenomenon that has long perplexed scientists and posed significant threats to our comprehension of the universe's fundamental nature. Despite numerous efforts to solve this riddle, the answer has remained out of reach. From the Institute for Advanced Study in Princeton, Edward Witten has described superstring theory for the modern era, an idea that emerged by accident in the 20th century. However, recent advancements have breathed new life into the mission to comprehend quantum black holes. Several groups of physicists have independently announced significant breakthroughs, uncovering that string theory could provide a complete solution to the problem, albeit within a more restricted two-dimensional setting, rather than the full 10-dimensional model proposed by conventional superstring theory. This is an encouraging development. Yet, the search for an all-encompassing solution continues to grapple with complexities, significantly hindering the quest for a theory of everything. Still, it calls us to investigate the darkest corners of the universe, where the lines separating reality from theory blur, and the secrets of existence await discovery and analysis. Black holes carry profound implications for our understanding of the universe, challenging our notions of reality and raising deep questions about the very nature of existence. The interaction between black holes and other astronomical phenomena, such as neutron stars and gamma-ray bursts, reveals the intricate processes operating within the cosmos. These cosmic interactions, particularly those involving black holes, have pushed the boundaries of astrophysics, forcing scientists to rethink the foundations of space-time, energy, and matter. Each new observation, whether it's the detection of gravitational waves from colliding black holes or the imaging of event horizons, provides a fragment of the puzzle, a glimpse into the grand tapestry woven by the universe. Moreover, the convergence of observational astrophysics and theoretical physics has led to remarkable synergies. Instruments like the Event Horizon Telescope and space observatories such as LIGO and JWST are not just validating long-standing predictions, they are also revealing anomalies that push existing theories to their limits. These moments of tension between theory and evidence often serve as catalysts for revolutionary thinking, an essential process in the evolution of scientific understanding. As we deepen our exploration, quantum gravity emerges as one of the final frontiers. It seeks to unify the chaotic elegance of quantum mechanics with the geometric rigidity of general relativity, two realms that, so far, coexist but do not fully communicate. String theory, and its broader cousin M theory, remain leading contenders in this quest, offering frameworks where particles are vibrations, dimensions are curled, and universes may exist in a multiverse beyond comprehension. Still, challenges remain formidable. The mathematics of string theory is abstract and vast, often venturing into territory where physical interpretation becomes murky. Predictions are difficult to isolate and even harder to test, with energy scales far beyond current technological capabilities. Critics argue that without falsifiable outcomes, such theories risk becoming elegant philosophy rather than empirical science. Yet, history has shown that the boundaries of today's imagination often define the breakthroughs of tomorrow. What was once the realm of speculation, black holes, gravitational waves, time dilation, has become demonstrable reality. In this light, the pursuit of a unified theory is not mere fantasy. It is a testament to humanity's relentless desire to understand the cosmos and our place within it. As we stand at this precipice of knowledge, with theories as vast as the universe itself and tools more powerful than ever before, the questions we ask grow deeper. What lies beyond the event horizon? Can time be bent, space folded, and dimensions traversed? Is the universe singular, or part of a greater, perhaps infinite, mosaic? These inquiries do not merely belong to physicists or philosophers. They touch something fundamental in all of us, a yearning to understand where we came from, what we are made of, and what ultimate truths await us among the stars.